Welcome back everyone, and in this video we just want to take a look if we apply the stuff that we learned so far to a real data set. And this is just like a short example. You will do more detailed analysis and more detailed examples in the tutorial for the course, but here I want to draw a bottom line here below everything that we learned so far by showing you a realistic example, and after that we'll proceed with the course material. Okay, so we are using a very popular data set. It's the California housing prices data set, and it includes the median house prices for California districts in 1990. And yeah, this is very popular and often used in many textbooks and so on because it is quite a good example. I mean, house prices is obviously something everyone can relate to. Everyone maybe has an intuition what is important for house prices, and yeah, that is why we want to take a look at it. And as it is so popular, it's already included in the sklearn package, so we can download it directly, and I think this is already a cleaned version of the data set. You find the example that we're discussing here in the collaboratory folder, in the lectures subfolder, and here it's the define for neural networks California housing. Actually, this kind of a playing ground where I tried different things. What we can do, or what we typically would do if we would conduct such an analysis in reality. Of course, there are many other things that we can do, but this is, just to give an idea. And as always, you're welcome to copy the code and play around with it and maybe add some interesting stuff and so on. Okay. But yeah, this basically grabs the data set, and I transform it here to a pandas data set because that is something that we will typically use. And then here we can take a look at the first 5 observations from the data set. We can see that there are certain feature variables. So for instance, the median income in this district, and then the house age. I mean, this is always, not a single house perspective. This is always the perspective for the houses in this district. And then we have the average rooms, the average bedrooms, the population in this district, and the average occupation, which I guess is related to especially if you are renting a house. Then I think it's probably I'm not quite sure, to be honest, what the occupation is. Maybe how many people are living in that house. Okay, so that makes more sense to me. And then latitude and longitude, which if we combine them, exactly tell you where the district is or where the houses are located. And then we have the median house value. I don't know in which unit this is given, but the higher, obviously, the more expensive, or the higher the price of the house. Now, if we take a look first at my collaboratory folder, then what I typically do, if I have a pandas data set, I use the info method because it shows you how many entries are there in the data set. Here we can see that it's approximately a little bit more than 20,000, and it shows you also the data types of all the variables, so all floating point numbers here for each variable. That means each variable is very likely a numerical number or like a number, a real value number, and a non-null indicates that there are no missing values, because if you would have, I don't know, here 20,000 and you have here 19,000 non-null, that means 1,000 observations are null observation, and a null observation is something that we typically refer to as a observation which is not observable, so it's not known to us, so it's not available. Okay, then it also shows you the memory usage here. This is especially relevant for bigger data sets and may show you how much of your computer or it may gives you an indication if your computer is capable of handling this data set. So in this case, it really should be no problem also if you do it on your local machine. Now, what I want to do or what I often do first, especially if I have many different numerical features, is I take a look at the box plots, or you could also alternatively take a look at violin plots for each variable, because this gives me an idea if certain variables may be plagued by outliers, or not plagued, but maybe exhibit very skewed distributions. So for instance here, with respect to the population, that seems to be the case. So we have a few populations that really, or a few districts with really high population, but obviously we have also the majority of districts which have rather low population. Then here we have some form of regression type problem, because the house price is simply a numerical number, or like a real valued number. As it is a price, obviously it should be higher than 0, but we will treat it as a real valued number somewhere on the value range of real valued numbers. And if we have a regression type problem, what I think can be informative is to take a look of the correlation between the feature variables and the target variable, but also the correlation among the feature variables, because this also gives an indication if it is really necessary to include all the feature variables. Because if we have highly correlated feature variables, it may be sufficient to only take a few of them, because the other feature variables do not really provide any extra information. Here, the pair plot is something I like to use, but it is kind of computationally quite intensive. So if you have bigger data sets, I would directly go to the correlation heat map. But the pair plot, for instance, here, as we can take a look here, here is probably what is most interesting for the median house value, like the pair plots between the feature variables. And here we can already see that obviously there is some kind of relationship between the median income in a certain district and the house value of, or the value of the houses in this district. There seems to be something going on also with latitude and longitude, but this is rather nonlinear, I would say. And for instance, this indicates to me that there is probably not a big relationship, at least on a linear perspective, between the age of a house and its price. And more or less the same information is shared in a heat map of the correlation. So the input of this visualization is the correlation between all variables, and here you can see with the color scheme in which value is given for each pairwise correlation. So for instance, obviously a variable correlates perfectly with itself. So here on the diagonal we have values of 1, which are indicated by the darker blue color. But for instance, here with a negative, quite negative value, we would have here, so that means there is very negative correlation between latitude and longitude here. Obviously, it doesn't need to make sense all the time, but it can be interesting. For instance, here we also see that there seems to be quite a high correlation between the income in a certain district and the house value. Then something else which I really find interesting, especially for this example, and to be honest, I've stolen it from somewhere else and I will show you where. But here, I mean, we all know so far, I think that not only like quality of a house or the size of a house really depends when it comes to determining its price. It's in many cases, it's rather the question, where is the house located? Okay, think about for instance, if you're in Germany, Munich or Frankfurt, there are really houses of bad quality which are worth a lot because they are standing in Munich or in Frankfurt, okay? And if we take a look here at the longitude and latitude as on the x and y axis, and then we plot each observation and use the price of the house in order to determine the color of the point here. So for instance, and we can see here red values are high values, so high house prices, and the blue ones are the ones which do not exhibit a high house price. And so for instance, this dot here would correspond to a district which is exactly here in this area, and where we have a rather low or moderate average house price value. And if you already have maybe in mind where California is located, then you already may have a good guess what is happening here, because we can see the house prices are obviously the highest in this area and in this area, and these are coastal areas, so close to the sea, and especially where we have the dark dot color, then this is like in the city centers, okay? But I've already told you that I've stolen this. So if you do not know this site, it's Kaggle. Kaggle is really interesting for everyone interested in data analysis. Basically, this is a web page where you can, where data is shared by many different people, and you can also find like tasks and challenges corresponding to data analysis. But also for each data set, you will find a code that is provided by other people and showing interesting stuff in some cases. So for instance, if you take a look here at the California house prices and I take a look at the codes here, what I always do is I filter here for the most votes, because most votes also to me indicates that this is a code many people have used or at least analyzed or looked at. And here, if you take a look at the geospatial feature engineering and visualization example and scroll down a little bit, then we can see that the person did not only exhibit or did not only create the plot in the way that I did, it also used the California map here. And so this makes it even more clear. Or in the last step now, if we simply go to Google Maps and search for California and take a look, then we will see, oh, okay, the areas where the red dots are Los Angeles and San Francisco, and like here is the coastal line. And now again, if we take a look here, I think this makes sense, and this really highlights the importance of where a district is in order to determine the value of its house prices. Okay. What I also like to do, but it does not necessarily make sense to you at the moment with your methodological knowledge, is I also like to use dimensionality reduction techniques in order to reduce the dimension of the feature variables to a dimensionality that we can still plot. And then again do the same as here, so use house prices to indicate the color values. So first of all, but it really does not need to make sense to you at the moment, but what I do now, and I already decided to do this here because I think this is really interesting, especially before we are trying to estimate any models or stuff like that. Here we have, let me quickly count it, 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, 9. So we have 8 feature variables here, and so if we want to achieve something similar to this here, we need to condense the information that is included in the 8 feature variables into 2 variables, okay? And this is a task that is can be achieved by so-called dimensionality reduction techniques. And what's the idea behind this is, we try to condense the information that is included into the 8 feature variables into 2 new variables that are constructed by an algorithm and include observations that do not appear in reality, but those pseudo realizations are generated in a way that they still include most of the information that is given in the original 8 variables. Okay, so that is like the idea of it, and there are different methods behind it. One of the most popular ones is the principal component analysis, which is based on linear algebra, and but it rather only includes the it's based more like on the assumption of linear relationships between feature variables. Then what I also use is the TSNE. It stands for stochastic something with neighbor. Oh, sorry. Let me just take a look. But it's always the T distributed stochastic neighbor embedding. Sorry about that. I always use the TSNE as an abbreviation. And also quite popular is the UMAP, which is given in the UMAP package. And you can see that in each of the, depending on the techniques we have here, the plots, they look different, but the idea of all of them is all the same. So we try to condense the information which is given in the feature variables here, which is here the X data, and then I condense it to a two-dimensional, to 2 dimension, which means we condense the information which is in the 8 feature variables into 2 variables. So then we have 2 variables, and the values of the first, as I said, a variable which doesn't exist in reality, of the first variable are given here on the x-axis and on the y-axis. And then again, I use the color in order to, or use the housing value in order to derive the color. So the higher the value, the more yellow it is here, and the lower the value, the more it turns into a darker blue. Okay, and I only want to do this because our model can only succeed in predicting something if there is some form of relationship. We're not sure about the relationship, but for instance, if we take a look here at this visualization, so here we use the TSNE algorithm in order to determine 2 variables which contain information of all the 8 feature variables. And now if you plot this here, then we can see that there seems to be some kind of relationship, because if in the middle here we have like the lower values or the houses including the lower values, and here we have houses with higher values, and also here we have houses with higher values. If there wouldn't been any relationship, then the colors would be mixed here, and there wouldn't be any systematic behavior of the coloring scheme here. Okay, so as I said, I do not really want to go too much into detail here, but in many example codes on blogs, you will see these dimensionality reduction techniques of the TSNE and especially the UMAP. And the idea behind is to just, in the best case, if you would be able to visualize the relationship between the 8 variables and the house price in a figure, then we would not need to do this. But we as humans are bounded to 2 or 3 dimensions when it comes to visualization. So in the first step, we try to condense the information which is given in many variables into a dimensionality that we can visualize, so 2 or 3 dimensions. And that is succeeded here by the dimensionality reduction techniques. And then we take a look if we can find some systematic pattern here when it comes to the information which is given in the feature variables and the house prices. The concept of dimensionality reduction may be more clear to you once we discussed the autoencoders. And yeah, we will do this during the semester. Autoencoders would also be a possibility that we can use here, or the principal component analysis could be considered to be an equivalent to a autoencoder which only uses a linear or affine transformations when using it, when creating the autoencoder. But we will come to that during the semester. Okay, but like the bottom line here is there seems to be some systematic relationship between the feature variables and the house prices, and this is an important news for us, because then now we're good to go, and it really would make sense now to create a model which uses the information of the feature variables in order to determine the house prices. Okay, and for you at the moment, really like the next 3 steps are the only important thing. All the other concepts in this Colab here is only something to play around and to already get you a realistic point of view on what you typically would do during analysis. Because so far we have the data, right? Okay, so that is now where you're standing. Then if you want to estimate a neural network, evaluate also if it's possible to make good estimations for unseen data, you need to split the data set. Then as we are working with neural networks, we need to scale the data, so bring all the feature variables to comparable numerical ranges. then we need to define a neural network, and then we need to estimate it, and then we can take a look at it. Okay, so and that is like what that should be your takeaway from this video. This is where you should focus on at the moment. Okay, so here we use the train-test-split function, which randomly draws observation and puts them into a test set and into a training set, and the remaining observations are then given in the test set. Here we can determine the fraction, so 30% of the data should be included in the test set, and 70% should be included in the training set. Here I set the random state, so that should we always get the same split here. If it doesn't really, it's not really something that you need to do. It's only if you really want to reproduce the concrete split that we use in this example here. Now, at first step, I take the raw data and I divide the feature variables from the target variable. So here, feature variables and then the house price as the target variable. And then I use like a standardization scaling, so the mean variance scaling or the mean standard deviation scaling. And I always only use the mean and the standard deviation from the training data, because I always want to treat this test data and I never want to use any information which is given in the test data for something that we'll also use for training the model. Okay. Also, I scale here the dependent variable, or the target variable. That isn't really what you need to do, but I think also it doesn't hurt. And in my understanding, it further creates numerical stability. Okay, or it enhances, or it can potentially stabilize numerical stability. Now, just be aware. So this is like the rare data, and then with this added symbol here, this is the standardized data. So basically, what this does here, the fit function only determines the arithmetic mean and the empirical standard deviations for each variable, and then we can, when we call transform, it simply does the calculation per variable. So realization minus the arithmetic mean divided through the standard deviation. And if we do this for the test data also here, then it still uses the arithmetic mean and the standard deviation that we calculated here from the training data. And this is what I mean with, I do not want to use any information for the test data except, or I only want to use information from the training data also for the test data. Okay, sometimes it makes sense also to again take a look at the box plot for the scaled feature variables, because actually this is the variables that we are used to, or like the realizations that we're going to use for for estimating the model. And especially as we have a standard scaler here, and for instance the population has been quite a skew distribution, and maybe all these other, especially where we can find here many outliers, are all variables that exhibit a skewed distribution in original data. And if we have too many outliers here, it may be a good idea to replace the standard scaler by a scaler which is more robust to outliers. So the quantile transformer, for instance, could be an alternative choice here, but I decided to use the standard scaler here because this is something that we see most often. And but I just want to create your awareness from the beginning or from the start. Never only use something because everyone uses it. Please feel free to play around here and use different scalars and see how this impacts your results, because it is not always trivial, or it's not always nothing, and sometimes decisions like this here can have a big impact on your final results. Okay, so like this is the first two steps here. First of all, we splitted the data into training and testing data. Second, we scaled the data. And now we are good to go. We have the inputs, we have the data in the form that we're going to use for estimating the neural network. When using TensorFlow or Keras, then I think the user-friendliest way of defining a neural network is the sequential function, because here sequentially you just add the layers. And what I always do, and it's not mandatory, but I think I like to separate the step, is first I create an input layer that is only provides the input shape, and the shape here, it means that each realization we will have 8 feature variables. So I just say here the length of the housing data set columns, except for the last one because it's the target variable. So this is, you could also write 8 here, okay? And then I add here a dense layer with 10 neurons and a sigmoid activation function. And I also use a dropout here, which I explained in the last video. And then, as we have a regression type problem, we need a single output as a prediction for each realization. And this shouldn't be transformed in any way, so it should be a real valued number. That is why we do not need to set an activation function here, because if we do not define an activation function in a layer, it will assume to use the affine transformation. Okay, so this is how we define the neural network. This also will be explained in way more detail in the tutorial. Then we need to compile the network. So we need to tell the network which loss it should minimize when calibrating the network. And also we hand over the optimizer. So I choose here to use the Atom optimizer. Feel free to take a look at the TensorFlow or the Keras documentation. There are many different optimizers available, and yeah, also this may have an impact on your results. Now, once we've done this, then we finally can fit the data, and here is we provide the data that is going to be used for fitting or for calibrating the parameters. Here I set the epochs to 20. An epoch is, it includes multiple iteration steps of the gradient descent method, because it also we have a batch size here. So what it does, if you do not say anything, I would say the default setting of the batch size is 32. So what's happening in a single epoch is always 32 random observations are taken from the training data. Then for these 32 observations, the gradient information is derived and used to update the parameter estimates. And this is done here for 452 times. That is, I think it's approximately the amount of data that we have divided by the batch size. So one epoch here includes 452 iteration steps, always using 32 randomly drawn data points. Okay, so but this is really detailed knowledge, but I just want to make sure that you maybe heard about it. And also we have directly the possibility here to hand over the validation data, which is not going to be used for calibrating the parameters, but which is evaluated during training. And then if we, if we press play here, then we can see what happens during training, and we can see that the loss for the training data seems to be reduced during training, and at the same time the corresponding validation loss of the validation data also gets lower, which is something that we want to see. Also visualize it here, and this looks quite good. We could think about it training a little bit longer, such that we are, like ending up at a plateau here. And yeah, like what we want to see here is a progression like this, ending up in a plateau for the loss and the validation loss. Okay. Then last but not least, we want to take a look. So this is like the loss value is already an indication how well it works. This is the mean squared error. And what I also, or for regression type problems, what often is used is the R squared measure or pseudo R squared measures. So I define this function in order to create these values, the R squared value for the actual realizations of house prices and the corresponding predictions. So what I do here is I first make a prediction with the trained neural network. then the output of this, or the value of this prediction, is like the scaled version of the original target variable, which is why I use the inverse transform method of the scalar that we defined in the beginning when scaling the data. And this brings us the predictions that actually correspond to the real house price values. And the R squared measure, just to make sure, squared, I think you should know it from regression type of problems, is you have the 1 minus the unexplained variation in relation to the total variation. Let's just take a look. I think Wikipedia has a formula also. Okay, so this is why I want to show you. So what we have, usually we have here the squared deviations of actual realizations minus the predictions. And here we have the squared deviations of actual realizations minus the average value. So what's behind, the idea behind here is, here the average value could be seen as an unconditional prediction. So we simply to predict the house price value, we take the average of all house price values, no matter the information of the feature variables. So that is why I call it an unconditional prediction. And if the information provided by the feature variables, so if we go to a conditional perspective, so if we use more information that is available, and if this information helps to improve our predictions, then obviously the squared deviations between the conditional predictions should be better. So the squared deviations should be lower. So this should be something which is obviously below 1. And the smaller this fraction is, that indicates that the better we are with our conditional predictions, comparing them to an unconditional prediction. So 1 minus this value again is a value which is the better, the more close it gets to 1. Okay, so here we have, if we calculate this for our example, then we have values which are close to 70% for training and for test data as well. And I would say this is quite okay. So that's the problem about the R squared, because only in a perfect world the model is able to perfectly capture the actual realizations. In reality, this will never be possible. So the real value, the real best value, is not really 1, and we do not know the real best value that we could achieve by using certain feature variables, because we do not know how exactly the reality looks like. Okay, we only model it. But nevertheless, I think this like 70% with my experience tells me this is quite okay. If we quickly go to the end of the file here, what I always take a look at, and I think this is more informative than the R squared itself, is the prediction and realization plots. So it doesn't matter if you plot the prediction versus the actual realization or the other way around. Here I use on the x-axis the prediction, and I plot them versus the actual realizations on the y-axis. I do this for the training data and the test data. This is here just with another model, but the principle stays the same. So in a perfect world, all points should be on the diagonal line with a slope of 1, because that would tell us if I predict a value of 2, then it is a value of 2. If I predict a value of 3, it is a value of 3, and so on and so on. And here you can see still the model, it looks quite okay. Yeah, we would never expect the model to be perfect, but the majority of the points should be, I don't know, somewhere close to the diagonal line here. But we also see something here that wasn't exposed earlier in the analysis, because here on the y-axis we have the actual realizations and they stop at 5. So they seems to be truncated. So that means truncation is something which is quite threatening from a statistical perspective or from a modeling perspective, because it means even though maybe the house prices in reality have been higher than 5, for instance 6 or 7, then the people gathering the data for certain reasons may have said, okay, we even though all values that are higher are are given a value of 5. And this can really mess up the estimations of our model, especially the parameter estimates that belong to the feature variables. But this is, to be honest, something for your statistics lecture and not for here. But like the bottom line is here, if we train a model, then it seems to succeed in order to generate some predictions that make sense. So we have values that are close here to the diagonal line, as well for training as well for test data. But this should also create awareness for this data set. In reality, if I would experience something like this, the next step would be a way to find out if I can get hands on the real data, so not the truncated one, or if there are any methods that allow to include this characteristic of truncation for the data, because this is something that really can mess up your results. Okay, as this video is already taking so long, I at the moment skip all the remaining parts which are in the collaboratory. Included here did other things such as cross-validation and also hyperparameter optimization, or at least tuning a little bit. You can take a look for yourself. I also try to comment it in a way that is understandable for people reading this information. But at the current moment, I think this information is still a little bit too much. Maybe it makes more sense in the end of the semester. And also very advanced stuff already, I think, is here, given the additional analysis with the feature importance. Even though I describe it in the beginning of the semester, I think this is something quite advanced and which takes some time to understand. So it's okay if you come back at the end of the semester and then take a look at the aspects or information provided here. Okay, so for the moment, just consider this to a short example how training a neural network looks like for real data, and just give this more room and space in the tutorial. And in the next video, we are going to continue with different architectures of neural networks. So see you soon, and bye bye.